Hi, this is an introduction to logic. I'm Mark Thorsby, and this course overviews the basics of categorical, propositional, and predicate logic. Today we're going to be looking at propositional logic. We'll be looking at how to conduct proofs using natural deduction, and today we'll be looking at the first 5 rules of replacement. We're using the Patrick Hurley textbook, but there's lots of other books out there. They differ and they vary to some extent, but ultimately they all essentially teach you the same thing. Anyway, guys, welcome back. This week, today we're going to be looking at the rules of replacement. Let me start off here by doing a sort of brief review and talking about what we looked at last time. In our last 2 videos here, we've been looking at how to conduct proofs. We've been looking at how to build proofs. And one of the things you'll notice, and I've been getting a couple of emails from people on YouTube here, different philosophers and different logicians do different things with their proofs, but fundamentally they're all the same thing. What we're basically doing is, again, we're using the rules of natural deduction. And using these rules of natural deduction, we are looking to see, or rather, using the rules of natural deduction, and there are many, many different rules. We're just looking at really 18 basic rules in this course. And using these natural rules of deduction, we're giving proofs for why certain specific arguments are valid. Where a valid argument, again, is an argument in which if the premises are true, it necessarily follows that the conclusion is also true. That necessary connection here is what makes an argument deductive. So that's what we're taking a look at. In the last couple of videos here, we've looked at a number of different rules. I just want to sort of lay out a couple of them for us today, just to remind ourselves, because you're going to see that in this video, even though we're looking at the rules of replacement, we're still going to be using the basic rules of implication and inference, which essentially consist of the modus ponens. And that looks like if P, then Q. If you have P, you can conclude Q. We're also looking at we'll also be using the modus tollens. That's what we did last time. Actually, in 2 videos ago, we looked at that. The modus tollens says if you have P, if P, then Q, and you don't have Q, it follows that you don't have P. We also looked at the hypothetical syllogism, and I'll also put HS here instead of writing the whole thing out. The hypothetical syllogism says if you have P then Q, if Q then R, you can conclude if P then R, where the Q essentially operates as the middle term. But after the hypothetical syllogism, number 4 here, we took a look at, we used the disjunctive syllogism. I'm sorry about that. Oh man, sometimes this Microsoft Word just doesn't work. Sorry about that. The disjunctive syllogism looks like this. If you either have P or Q, if you don't have P, it follows that you must have Q. Now let me say something about the word syllogism here, because I did talk to one of the people online from YouTube, in which there was another textbook that they were looking at, and they were using what's called the conjunctive syllogism. And I didn't know what they were talking about at first, but I do not know what they were talking about. In the particular book that they were using, a syllogism here in its basic format refers to any argument that has 2 premises and 1 conclusion. Any syllogistic argument. And a conjunctive syllogism would be any syllogism, any argument that has 2 premises and 1 conclusion, in which one of the premises had a conjunction in it, and that's what a conjunctive syllogism would be. In this video, or because we're using the rules of inference as laid out by Patrick Hurley, the disjunctive syllogism is going to refer to this thing in particular, whereas this other textbook was using a conjunctive syllogism, and that referred to really any sort of deductive argument with a conjunction in it. So we're a little bit more precise in this text because we're using each of these as rules as ways of explaining or detailing our proofs. Okay, number 5 is the constructive dilemma. the constructive dilemma. And the constructive dilemma looks like this. If you have P then Q and R then S, and you have either P or R, you can conclude that you must have either Q or S, right? That's the constructive dilemma. Oops, I'm running out of room here. Oops, sorry about that. Give myself a little extra space here. Okay, so that's the constructive dilemma. And then the other rules we looked at here, number 6, is we looked at the rule of simplification. Where simplification says if I have P and Q, I can always just conclude P, right? Because in a conjunction, in order for a conjunction to be true, both P and Q have to both be true. Thus, if I don't have this, P still remains true. Number 7 here is the conjunction. And the rule of conjunction says that I can always combine any two premises that are true. So if I have P and I have Q on separate lines in my argument, I can always combine them by using a conjunction. And then the last rule here, number 8, is the rule of addition. And the rule of addition, says that if I have P, I can always add a Q. Where Q could really be anything here, but I could always add something because the disjunction rule says that in order for this statement to be true, only one of them has to be true. Thus, if I know P is true, I can always add Q and it's not a problem. Okay, now the reason I sort of overviewed these are the basic rules of implication or inference is because what we're going to see today is we're going to still use these rules, but today we're going to talk about something brand new, and that's the rule of replacement. And the rules of replacement work differently than these rules of implication because in these rules of implication, each one of these has to be a specific line, and I conclude this, and so on and so forth. But you're going to see the rules of replacement really give me a lot more flexibility. Okay, and there's actually 10 rules of replacement in total. This video is going to survey the first 5. In our next video, rules of replacement 2, we'll get the other 5 down. But the rules of replacement are expressed in terms of pairs of logically equivalent statement forms, either of which can replace the other in a proof sequence. So what we have to do in order to use rules of replacement, we're going to introduce this new symbol, the symbol of a double colon, the double colon. And what the double colon means is it's used to designate logical equivalence. Now, it's a metalogical symbol, and that means that, well, I won't actually go into explain it, but it's a metalogical symbol that does not assert that things are logically equivalent, but that statements are logically equivalent. And that's an important feature because obviously in ordinary language when we translate it, even though the forms of statements may be logically equivalent, the things themselves, the things that our statements refer to may not be logically equivalent. But ultimately, in order to conduct proof, we don't have to worry about things. We're worried about statements, okay? And then finally, the double colon asserts that either side of the equation has the same truth value despite the truth value of the components, okay? So the next thing we need to know here is what we call the axiom of replacement. Now, an axiom, basically an axiom in any sphere, is something that you're going to use that you're not going to question. We're not going to prove that the axiom of replacement is true, at least not in this video. But we're just going to, an axiom is essentially an operative assumption that you take on and then you're going to agree to believe is true for the sake of the calculation. So this is an operational assumption. That and the reason we can't prove the axiom of replacement is because the axiom of replacement is the assumption that allows us to use the rules of replacement, which means that we can't use the logical rules of replacement to prove it because it depends upon it. And that you're sort of confused there, take a look at what an axiom is. Go to the internet, go to the Stanford Encyclopedia of Philosophy, look up axiom, and you'll see what I'm talking about. But here's what the axiom of replacement says. It says that within the context of a proof, right, within the proof, not within, right, ordinary language, so we're not talking about things, we're talking about statements. So within the context of a proof, logically equivalent expressions can replace each other. So how is this different than the rules of implication? Well, the rules of implication said that in the context of a proof was, well, if I have this premise and I have this premise, I can conclude this premise. But we're going to see that the rules of replacement allow us to take something like this, a whole premise, and just replace either all or one aspect of it rather than inferring from it, okay? And you're going to see what I mean here in just a moment. So this is the axiom of replacement. It's pretty critical. So let me take a look and show you what the rules that we're going to look at here. The first 5 rules of replacement are right here. And let me see, I'm going to try to explain them, but you're going to see that the best way to really get a handle on these rules of replacement is actually just to use them and actually just do the exercises, okay? Notice you'll see here we have our double colon, right? When what the double colon means, that it means this, that this statement here, which is not P and Q, is the same as saying not P or not Q, right? And DeMorgans rule here, and DeMorgan was a famous logician here, it can also be reversed, such that if you have not P or Q, you can replace it with not P and not Q. Notice that basically what happens, and this may look similar in algebra to what we sort of call factoring in a negation. Basically, if we have a negation here, and I'm going to use the first version here, but you can see it applies to either. If I have not P and Q, what I can do with DeMorgans is I can essentially move the negation in front of each of these, but then I have to switch the sign. So that means what I'll end up with after I do the DeMorgans is not P or not Q, right? And the same thing goes if I have, if in my parentheses I start off with the disjunction. So if I have not P or Q, I can factor in, I don't like using that term, but I think it's helpful for a lot of people, since most people have basic algebra skills. It turns into not P, switch the sign, and not Q. And that's DeMorgans. Now, what's important is just because I've done these in this direction, right, they can go in either direction. So if I have this statement, I can use a DeMorgans to get, I can replace this statement in a premise with this version. So they go in either direction. You can either go in this direction or you can go in this direction. Either way. And that rule is gonna apply to all of these. You can always go in either direction. Okay? And so DeMorgans basically says that if you have a negation outside of parentheses, if you want to put it inside, it goes to both of the variables, but the sign switches. And for the DeMorgans, it only works for conjunction and disjunction. And that can be explained by ultimately taking a look at the bivalent properties, that's the truth and false properties of the logical operators. But we're not going to do that right now. But it's an important rule. And here, eventually, you're just going to have to memorize the DeMorgans. Okay, commutation is a really easy one. And commutation basically says this, that if I ever have a statement with the disjunction or a conjunction, I can always just switch the values around. I'm sorry, the variables around, right? So in this case, P or Q is the same as saying Q or P, right? And P and Q is the same as saying Q and P. And again, that's a result of the bivalent definitions of each of these things. And if you wanted it here, you could always do a truth table. And what you'll find out, and if you looked at our other videos, you'll notice that we actually talked about the definition of logical equivalence and how you can compare 2 different truth tables to discover logical equivalence. You'll find that for any of these rules, if you do a truth table, you'll find, and you compare them, that they're logically equivalent truth tables. And by the way, that means that in the future, we could always discover new rules and new rules of replacement, such that if we did truth tables and they were logically equivalent, we could actually literally make up a new rule and build going off of that. So the truth table means here is still very, very much pertinent, okay? So that's commutation or commutativity. I'm usually going to say commutation in here. You know, I'm going to let me clean this up a little bit. Let me just delete that. Okay. Okay, so that's commutation. It means you can just switch them around. So maybe I'll do this. Right. So commutation means you can switch variables But you can only switch the variables so long as they have a conjunction and a disjunction. Okay, and then DeMorgans rule isn't, instead of switching variables, that's when you move a negation inside or outside of parentheses. That says parentheses, I'm running out of space. But you switch the operator. Okay. And that, again, that only applies to the conjunction or a disjunction as well. Okay, and you'll see that actually all of our rules here only apply to disjunction and conjunction today. We'll see in our next video, rules of replacement 2, we'll start taking a look at the other rules in which we actually use biconditionals as well as conditionals. Okay, the rule of associativity. What does this look like? This rule, it basically says if I have P or Q or R, where I have brackets and parentheses, I can actually move the internal parentheses over, right? Notice that the parentheses are around the Q and an R, but that really means the same as if putting them in between the P and the Q and leaving the R on the outside of the brackets. So this rule here really allows us to move parentheses around. Right, it allows us to move parentheses around, and for the disjunction as well as the conjunction here, right? Notice P and Q and R can be the same as P and Q, close parentheses, and R. Okay, so associativity is about moving parentheses around. Now, here's distribution. Distribution is a little bit trickier because it looks sort of like associativity, and it also sort of, well, it looks sort of like associativity, I guess. But it's a little bit different because you'll see that we're going to move around some signs. So if I have a statement that says P and Q or R, that's the logically equivalent of saying I have P and Q or I have P and R. Because notice, if I have the disjunction here, the conjunction here, that means that I must have either P and Q or I must have P and R. And that's exactly what the rule of distribution allows us to do. Note, and of course it goes the reverse way too. I don't necessarily have to go from this direction, I can replace going this direction as well. And the same thing over here. If I say I have P or I have Q and R, that's the same as saying I have P or Q or I have P or R. And that's exactly what this statement says here. So what exactly does the rule of distribution allow us to do? It allows us to move parentheses and change signs. So it's similar to distribution, except it's when it occurs when I have both conjunction and disjunctions. So it allows me to move parentheses around, right? But for those statements that have both conjunctions and disjunctions, and also notice that this statement has 3 variables, whereas this statement has 2, this statement has 2, and then this statement has 2. So you are not going to use distribution unless you have 3 variables that you need to work with and you have both a conjunction and a disjunction. And the last rule, which is really, really easy, is called double negation. And double negation basically says that if you have P, that's really the same. That's logically saying that I don't have not P, right? So that's saying, for instance, imagine if the P stood for a proposition that said, Joey likes ice cream, right? That saying Joey likes ice cream is the same as saying it's not the case that Joey does not like ice cream, right? So double negatives. Now, of course, we're always taught in English class never to use double negatives, but you can see here the reason people do use double negatives is because fundamentally we recognize that double negative, something that's negated twice, ultimately turns into the same. And this is the same as saying if I have, if I have 2 negatives in math, it's sort of similar. Well, no, actually it's not similar. But in terms of ordinary language, it should make total sense, okay? So what I want to do now, is I want to do a couple problems here. And these problems actually come from the textbook, but I want to do them for you. I have 4 different problems that I want to do with you. I'm not sure where all these little lines came from, but let's just ignore that. Okay, so let's do this problem, because you're going to see that we're going to have to use all of the rules of replacement, as well as some of our other rules, our earlier rules of implication, are still going to be utilized here. Okay, so now let's start with this. You can see here that my conclusion is negative b, right? And let me say something as an aside, right? Because some people are going to write their proofs differently. I actually think that the way Hurley writes his proofs here is the best way to do it. And the reason is because I think it's the clearest way for people to see what you're doing rather than other texts, or at least a version of Hurley. I think Hurley does a good job here. So we're going to continue to write the proofs the way we have been in this video, or this video series. So our conclusion here is negative b. So first thing to do is say, okay, I have a b here, but it's negated, right? So what should I do here? And there's lots of different things I could do, but you can see here I could do a DeMorgans right here, right? Because the rules of replacement, and I'm just going to do that right now. The rules of replacement say that if I have a specific spot, I can actually replace that using the rules of replacement. And I'm going to do a DeMorgans here because, and I know that it's hard to see all the, let me see if I can actually scroll up here so we can look at those rules as we go. Here we go. Here's the DeMorgans. Let me make it a little bit higher. So here's the DeMorgans, so you can see what we're doing while we do it. Okay. Notice for the DeMorgans, right? It basically, right, not B and C. That's basically this, which means I could replace this with this right here. So that's what I'm going to do for Rule 3. But remember, rules of replacement means I still have to keep my A and conditional going. So let's write that down. So that's going to be A. That's going to be A. Then, and here's where I'm going to replace it. Parentheses, not B or not C. Okay? And so I'm going to write line 1, DeMorgans. Right? And this is what got changed. This just carries over identically. So always make sure to do that, right? You may do a DeMorgans and forget to write this, and you'll completely change the value of your equation. So what should I do now? Well, you can see here, now I have my negative b, but I need to unlock it, right? I always think of it, another way of thinking about this is, I used to play Nintendo and Zelda a long time ago in the 80s here, in the late 80s. And I always think of unlocking different levels. This is a modus ponens ultimately. If I could get A, I can unlock through the rule of modus ponens the not B or not C. How can I do that? We'll take a look at line 2. I have A or C. Let's use the rule of simplification. And it may be helpful ultimately for you to have all the rules written out for you next to you as I'm doing this, because it will take too much time for me to show you constantly what the rules are. So I'm going to do A, and I'm going to use line 2, simplification. So I'm going to put simp. Now that I have my A, I can put it in here and unlock this. So that's going to be line 5, not B or not C, right? And that's lines 3 and 4, modus ponens. Right? And notice that I don't have the parentheses anymore, because remember, the parentheses exist, the parentheses, the brackets, and I don't know what they're called, but the squiggles here. These things exist in order to help us always understand what the main operator is. Right? To understand what the main operator is. And so the main operator in this, right, the parentheses allow me to see that this is the main operator, but now that I've unlocked it, there's only one operator, where, I mean, there is the negation, but negation only applies to what follows immediately after it, which means that I don't need the parentheses, so I didn't rewrite them. You can, right, we can put them there if we want, but it doesn't really add anything. It just, I think it makes it a little more confusing. So let's move here now. Now that I have not B or C, take a look at C here, and I have the negation C. Remember there's the rule of the disjunctive syllogism. Whenever you see a disjunction, think the rule of the disjunctive syllogism. So the first thing I need to do is number 2, I need to commutate these. I need to switch them around because, strictly speaking, the rule of simplification says that if I have P and Q, I can always conclude P. So line 6 here is going to be C and A, and that's going to be line 2, commutation. And now line 7 here is going to be C. That's line 6, simplification. right? And the reason I wanted C, right, and by the way, I need to also commutate these as well, but you'll see why in just a minute. Well, let's go ahead and do it here. Line 8 here is going to be, I'm going to commutate these, I'm going to switch these to not C or not B. Oops. Right, so that's line 5, commutation. Right, and some of you may not directly and immediately see why I'm doing what I'm doing as I'm doing it, but the more you do these problems, the easier it will be for you to see what we're doing here. The next thing I do is, because I want to set up a disjunctive syllogism here, and if you recall, the disjunctive syllogism is if you have P or Q, but you don't have P, you can conclude Q, right? What's my goal? Not B. This is my goal right here. I'm really close to getting there. So what I need to do is get rid of this C somehow. So let's use this rule. And I have a C here, but I need to do a double negation. So line 9 here is going to be not C. I'm just replacing the C here with this. So that's line 7, double negation. And now you can see here that I had my not C, but now I have my P, but now I've negated it, which means line 10 is going to be not B, and that's going to be lines 8 and 9, disjunctive syllogism, okay? And that's the proof. You see now that I finally got to the not B, I finished the conclusion, and that's the proof of its validity, okay? So you can see how these rules start working, but what I want you to see here to really catch here is when we did the rule of replacement here, we only replaced part of the line. Right? It's possible we could replace the whole line, whereas, for instance, C, right, this was the whole line, and we replaced the whole thing with that. Oops, you can't see that anymore, but that's all right. We replaced the whole thing, right? So that's an important feature. So let's do another problem here. And by the way, as you're watching these videos, you may find that you don't, if you sort of see how we're doing these, obviously feel free to just stop watching the video and go ahead and do them. I'm just doing these practice problems over and over so that people can really see again and again how to do these problems. And I also encourage you to write the problem down, pause the video, and then see if you can do it on your own. Okay, so let's take a look at this problem. What do we have here? Okay, this says, the first premise says that I have D and E or F, right? And I have not D or not F, okay? Now, what should we do here? My goal is to get this by itself, which means here's my D and here's my E, but I got this parentheses here. Wait a second. Didn't we have the rule of distribution? Scroll down here, because notice I have 1, 2, 3 unique variables, and down here you need 3 variables, and it allows me to move my parentheses around, but more importantly, it'll allow me to get that D and E together, just like this. So I think the first thing we should do here is probably do line 3 here. Let's do a distribution. So how do we do it here? Remember, it says if I have P and Q or R, then I can say I have P and E or D and F. So that's going to be D and E or D and F. Okay? And that's line 1, distribution. Okay? You can see here, all I've done is I've just replaced these. I've just replaced them by moving around the parentheses and using this rule here. Okay, so let's go back up here. What's the next thing I need to do? I need to get this thing by itself, which means, take a look, this D and F, I need to get rid of that thing so I can get this by itself. How can I do that? Wait a second. Go back and take a look at this, right? Okay, so I need to get this by itself, but wait a second. Couldn't I use it DeMorgans again? You're going to see that whereas the modus ponens is really important in the rules of implication, the DeMorgans is utterly critical in this case. Because notice I have a not D or a not F. If I can get DeMorgan says, right, if I want to sort of take out this negation and add in parentheses, I'll switch the sign to a conjunction. That's exactly what I have here. So line 4 is going to look like this. Whoops, what is that doing? Okay, line 4 looks like this. I have not D and F. That's line 2 DeMorgans, right? Now, notice Remember that rule of disjunctive syllogism again, right? P or Q, not P, therefore Q. It looks like I could get rid of this if I commutate this first. So line 5 here, let's do a commutation. It's going to be D and F, or D and E. And that's line 3, commutation. And now I have it set up. Remember the rule, this here is basically a substitution instance of a P, right? So, and here's my not P, so I can get rid of it. So what's line 6 going to be? Line 6 is going to be D and E, right? Lines 4 and 5, disjunctive syllogism, okay? So that problem really wasn't difficult, but you can see what it required us to do was to first off see that we could do a distribution here, and then second, that this is an instance of a DeMorgans possibly. And so that's what we did. So that's the proof for that example. I have 2 more examples here, and then we'll take a look at some of the homework exercises. Here's another example. This is G and H, or G and J. And here's G or K, then L. And my conclusion is L, which means, okay, so I need to get this. It's right here, which means I need to get this thing, and then I can use perhaps some modus ponens to unlock this level, right? I don't know if that's helpful language for you, but I think it is. But you can see my G or K will have a G up here. Wait a second, I don't see a K. How the heck am I going to get a G or K? Okay, well, let's see what we can do with this problem. Well, and since, of course, we're doing our rules here, let's take a look at these rules down here. Notice this looks like an instance here. And that's one of the things you can do here is if you have your rules with you, you can just sort of say, does this look like I could substitution instance here, right? I have a 1, 2, 3 unique variables with the conjunction, and then, with the disjunction, and then 2 conjunctions. Let's do a distribution and get it over here. So line 3 is going to be G, right? Because basically I'm pulling out the G's. Right, let's do it over here. I'm pulling out the G's, and then I'm just going to combine these as I have G and H or L, and that's what it's going to look like. So let's write it down. That's G and H, or L, and that's line 1, distribution. Notice that in the last time we used a distribution, we started with this and substituted this. This way we've reversed and gone the other direction. Okay, what's next? What can I do next? Well, let's take a look. Line 4 here is, if I can notice there's no K in the first line, so the first line we're done with. Wait a second. If I can get G by itself, I could use the rule of addition and just add K. Let's do that now. So that's going to be G, and that's line 3, simplification. Because remember, once you have a conjunction, that means that I can just cut this out and just keep this. Now, line 5, let's see. Okay, sorry about that. I got a little interrupted there. My son was crying. Let's go back here. So I simplified G. So now that I have G, let's just add K. Because remember, if I can get this thing, I can unlock the L and finish the problem. So let's just add it using the rule of addition. So that's G or K, right? That's line 4, addition. And now that I've added it, I can use the modus ponens and unlock L, which means line 6 is L, right? And that is lines 5 and 2, modus ponens, okay? Not a very difficult problem, but you can see it required me to do that distribution. Now you're going to see, I'm going to go over a couple strategies here. We'll do one more problem, then I'll go over a couple strategies that may help you in terms of figuring out when to do which problems. So let's do this problem here. What's this thing? I have F and G, or B and G. Notice I have 1, 2, 3 unique variables, which means I've got it. This needs a distribution here, but you can see I'll have to do a distribution and then a commutation to get this, which means I'm probably going to be looking for something that looks like this. Now, so what can I do here? Well, let's see. Let's try to unlock this. I'm not exactly, and I'll be honest, I have the book here, and I can actually look and see what the answer is, but I'm not looking at the answer. I'm doing this problem with you so you can see what it's like to actually do a proof. Okay, so let's take a look here. I don't exactly see, it's not at least utterly apparent to me what to do. I have some ideas, but let's sort of look at the problem. It's not quite clear here, but notice if I can get K, I could get this F and B. Here's an F and a B. Here's a K here. Wait a second. If I can do a commutation and then a simplification, I can get the K and do a modus ponens. So let's do that. Line 3 here is going to be K and G. That's line 2, commutation. Line 4 here is going to be K. Line 3, simplification. Okay, now that by itself, now I can unlock this, right, using the rule of modus ponens. So, line 5 here is going to be F or B, right? That's lines 4 and 1, or actually 1 and 4, modus ponens. Okay. Now that I have the F and the B, now remember, I think what I need is something like this. I think if I can add this, I'll be in good shape. Wait a second. Take a look here. What if I add the G? Because notice I have the G. I have a G here. Let's simplify line 2. So line 6, let's just get G by itself, and that's line 2, simplification. Okay, now that I have that, let's conjoin these two together using the rule of conjunction. So that's going to be G and F or B. That's lines 5 and 6, conjunction. And I swear I'm not looking at the answers here. I mean, you can't know, and I guess you don't have to believe me, but I'm not. Okay, now that I have this, let's do a distribution, because don't I have this setup where I have a conjunction, close parentheses this, and I have 3 variables. So I'm in good shape here. So let's do that problem now. Let's do a distribution, which means I'm going to end up with this, right? I have G and F, or I have G and B. Now notice, it looks really, really close to this. The difference, though, is that the G is in the left-hand side and when it should be on the right-hand side. So I can commutate both of them. And I guess there's some debate here about whether or not you need a line 9 and a line 10. I'm curious what Hurley does. If he solved this the same way. I'm just going to commutate both of them simultaneously because the rule of commutation applies equally. So which means I'm going to do this. F and G, or B and G. And that's line 8, commutation. And I really sort of did 2 commutations because I did one here and I did one here. But I think that works. And you can, it's still valid, I know that. So, and you can see here that's the conclusion we were after, which means we've proven the argument here, okay? Okay, so great, that one is done, valid. Okay, and let me see here, actually take a look at what does Hurley do? Okay, yeah. Hurley did 2 commutations, so I guess he would be mad at me. So you may want to do this, for instance, if you have a test, to just do 1 commutation per line. I sort of doubled up the commutations there because I did both of them. So Hurley has you do 2 different, so I sort of skipped a step and combined it, but it's still valid. And I think that if we just understand that commutations can be done that way, it's okay. But for those of you, so if you're taking my class, it's fine for me if you do that. But if you're taking another professor's class, that other professor may definitely want you to do only 1 commutation per line. But I did it twice. Okay. Okay, so those are the examples on how to do these problems. It's not too difficult. So let's sort of take a look at what are some of the strategies for using the rules of replacement. And I'm actually going to draw your attention here to the textbook and sort of show you, because these are the strategies that Hurley lays out, but it may be helpful for you. So let me sort of scroll down here. And notice here's that same problem we just did. See, I ended with line 9 because I did 2 commutations and he says only 1 commutation per line, which is probably better practice ultimately. So you probably should do that, but you know, when you're writing these things over and over, it seems sort of strenuous. Anyway, strategy 11. Here's a couple strategies. Conjunctions can be used to set up DeMorgans. So take a look. If you have two lines together and you conjoin them, I mean, if you have two negative premises, you can always conjoin them and then set up a DeMorgans. And you know what? Even if you just had an A and a B, you could also do a double negation on these, conjoin them, and then set up a DeMorgans too. But remember, if you do a double negation, I would still have not A or not B. So I would keep, then if you do a double negation, it would one of those negatives would still remain inside the parentheses. Whoops. Um, let's see, here's strategy 12. A constructive dilemma can be used to set up a DeMorgans rule. So take a look here. Here's a constructive dilemma, right? You have A, then not B, and C, then not D. You have A or C, which means you must have not B or not D, right? This can set up a DeMorgans, right? Because I can pull out that parentheses, change the sign, and I get this. Okay, strategy 13. You can use addition to set up a DeMorgans rule. Whoa, I don't know what just happened there. Sorry about that. And in fact, you can always use an addition. While I pull this up, you can always use an addition to set up a DeMorgans. And we actually did that in one of our problems, where I think we added a K, and then that allowed us to set that up. So, so we actually did that. So that strategy is not really that interesting for us since we already saw it. But it may be helpful to know these. Ultimately, these strategies are sort of hints. But if you just, I would encourage you, instead of thinking about the strategies, just practice these problems, and then you'll get to the place where you don't need the strategies. Essentially, you'll be able to know what to do simply because you've done it a number of times. So, but you can set up an addition in order to do a DeMorgans. Remember, since you can add anything, you can add that negative in there. Okay, here's a little thing about Quine. Okay, strategy 14. Distribution can be used in two ways to set up a disjunctive syllogism. And again, we actually just did that. These are really sort of annoying, actually, in the sense that, okay, it's obvious. You can see here, when we do the distribution on line 1, right, that allows us to do a disjunctive syllogism by getting rid of the A. That leaves us with the B or C. And here's another example of that. Strategy 15. Distribution can be used in two ways to set up simplification. Okay, so let's see what this person did. They've distributed line 1 here, and then because there's that conjunction, they can cut out one side of these, or commutate it and cut out the other side, and that gives you A or B, right? So you can simplify by doing a distribution. Remember, distribution only works when you have 3 unique variables. And here's another one. And so here's strategy 16, which looks sort of like the throw in the towel strategy, right? If inspection of the parentheses doesn't reveal how the conclusion should be derived, consider using the rules of replacement to deconstruct the conclusion, right? So you can always start with the conclusion and start thinking about how to use the rules of replacement. Let me see. I actually did this for you a little bit here, right? Remember when we first saw this problem, I said, wait, if we did a distribution on this, we would get, well, I was thinking in my head, we'd get this line, or something like those. We'd have to do a couple commutations. And then we could add it in, right? So one thing to do is if you can't quite see what to do, look at the conclusion, see what sort of rules you could use using the rules of replacement in order to maybe give you a hint on what to do here. Okay, so let's sort of take a look at some of the exercises. I'm not going to do 2, I'll just do 1 exercise from each of the first 3 sections here, just so you can get a sense of how to do this. And then we'll conclude this video here. Okay, so let's take a look at problem 1. Not too difficult, it looks like. What they're going to do is they're going to give you the premises, they're going to give you the rule that gets used, and what you need to figure out is what line they're going to do it with, and what's going to happen when you do that, what the resulting statement looks like. So this is clearly line 2, right? Because remember the DeMorgans rule, right? DeMorgans says that not P or Q is logically equivalent to saying I have not P and not q. I have this right here in line 2, which means this is going to go in line 4. So that's going to be, instead of p and q, it's going to be n and j, and so that's not n and not g, and that's line 2 DeMorgans, right? Not too difficult. It's just, in these first few exercises, they are actually fairly easy, but the thing is, they get you in the habit of seeing substitution instances, and that's really the critical component if you want to do well on these problems. Okay, so let's take a look at here. Basically, the setup for the second set of problems here is very similar. Let's do this problem instead. Okay. Okay, you can see here instead what they want me to do is I need to figure out what this line was and how this line got derived in order to get this, and then what rule and what lines got me to this. Now, I can see there's a g here. Okay, what am I going to do here? Wait a second. Take a look at this. I think I can do a modus tollens, right? I think what we need to do here is a DeMorgans and a modus tollens. Remember, a modus tollens looks like this. If I have P then Q, and I don't have Q, I can conclude that I must not have P, right? And then the DeMorgans, I won't rewrite it since you've seen it already. So it looks like this, line 2. It looks like line 2 needs the DeMorgans. And what it's going to, the resulting line would be not R or N, which is this thing right here. So this is my P and this is my Q, which means if I don't have this, I must not have this, which means I'd have not G. And so that'd be lines 3 and 1, modus tollens. Notice that in the homework section here, they're using all of the rules up until now. So we're slowly accumulating all of our rules here. Okay. Now, line 3 here, I'm sorry, section 3 is the part that really matters. This is when you actually have to begin to conduct proofs. And what you'll find is that the proofs get harder as you go through, right? Let's do problems 2 and 3 here, so you can see how to do these two problems. This first problem looks fairly tricky, doesn't it? And let's rewrite it over here. So line 1 here is not S. I only have one premise, not F and S. So how can I do this? This basically would be Shane's not going to the party, therefore it's not the case that Frank and Shane are going to the party. And when you actually say it like that, it makes sense, right? Even if Frank goes to the party or doesn't go to the party, Frank is not going with Shane because Shane is not going. So that makes sense. But how can I actually use the rules of replacement and implication in order to get this? Well, obviously my premise here is there's no F, which means how can I get that? Well, obviously I'm going to have to add it. I have to add that. So what should I add here? Well, notice I'm probably there's a negation here, but then if I just add negation, if I just add F, that's problematic because obviously this looks like I'm going to have to do a DeMorgans because I have a negation in front of a parentheses with the conjunction. So that means line 2 is going to be this, not S and not F. So line 2 here, this is line 1 addition. I added not F was my addition instead. Instead of adding F, I added not F. Now, some of you may be thinking, but you may not know, since you just made this up, that Frank's not going to the party. It ultimately doesn't matter because the rule of disjunction, right? If you go back all the way to truth tables and you did a truth table here, the rule of disjunction says that only one of these has to be true. Since this was our premise, we know that, or at least we're assuming this is true. Who cares what this is, okay? So line 3 here is going to be not S and F, right? And that is line 2, DeMorgans. But wait a second. See here, the F and the S are on the wrong sides. So let's just do a quick commutation. So that's not F and S. Okay, so that's the line 3 commutation. And that's the proof for that problem. Not too difficult, though I imagine a lot of you probably would have got stuck for a while on this problem, perhaps. So let's do problem 3 here. So we'll ignore this stuff. Okay, so my conclusion here is J. I want to get J by itself. Well, I notice J is over here. Wait a second. Whenever I see a J or K and L, that's 3 unique variables. This looks like a good instance of distribution, right? So let's start off by doing a distribution on line 1 here, okay? So that's going to be line 3. And that's going to look like this. Either I have J or K and J or L, right? And let's actually erase this. Get rid of that problem. Okay. So that was line 1, distribution. Line 4 here, remember I need to get the K by itself. The K's here, it's not in this. Wait, if I have a conjunction here, can I just get rid of that by simplifying? I can, so let's do that. That's going to be J or K. Line 3, simplification. Right, and that's because this was my P and this was my Q. And the rule of simplification says that if I have P and Q, I can always just simplify to P. So that means I end up here with J or K. Now look, I have line 2 is not K. Wait, I need to do, if I can do a commutation here, I can then do a disjunctive syllogism. So let's make that K or J, right? That's line 4, commutation. And then line 6 here, since I have not K, remember the disjunctive syllogism is P or Q. If I don't have P, then I have Q. So that means because I don't have the K, I must have J. So the answer here is going to be J, lines 2 and 5, disjunctive syllogism, right? You can see that really wasn't too difficult. Though I will tell you, even as someone who teaches this class every term, right, when you get to these problems, like problem 35, this is when it gets more difficult, and you may have up to 20 lines in your proof. So some of these are difficult, I'm not going to lie to you, but if you're preparing for a test and you have a test coming up, you really, really, really should just do all of these problems. Even if your professor doesn't assign them all to you, do them all. Because ultimately, practice, practice, practice makes the ultimate difference in terms of doing well on these problems, okay? So that's the rules of replacement. And then, of course, there's the translation problems. I'm not going to worry about those. And then they have even more sections here. But that's basically the rules of replacement. You're going to see next time we're going to do rules of replacement 2, and we're going to add in 5 new rules. So that's another reason why it's so important for you to actually practice these problems, because as we add more and more rules, it's going to get fairly complicated. So you want to get practice so that way these things are on the tip of your mental tongue or whatever, that could something like that. Anyway, thank you for watching the video. I'll see you guys online when we post rules of replacement 2. Okay,